groundbreaking study unveils universal laws of quantum entanglement across dimensions. Imagine a world where the very fabric of reality is intertwined, where particles can influence one another regardless of the vast distances separating them. This is the fascinating realm of quantum entanglement, a phenomenon that has captivated scientists and researchers alike. Recently, a team of theoretical physicists made a significant breakthrough by demonstrating that the principles governing quantum entanglement are consistent across all dimensions, utilizing a concept known as thermal effective theory. Their findings were published on August 6, 2025, in the prestigious journal Physical Review Letters as an editor's suggestion. This research marks a pioneering application of thermal effective theory within the field of quantum information, showcasing its potential to deepen our understanding of the intricate structures of quantum entanglement. Lead author Yuya Kusuki, an associate professor at the Institute for Advanced Study at Kyushu University, emphasizes the importance of this approach in advancing our grasp of quantum phenomena. In the realm of classical physics, particles that are far apart behave independently, acting as if they are isolated from one another. However, quantum physics reveals a different story. Two particles can exhibit profound correlations, no matter how far apart they are. This intriguing connection is what we refer to as quantum entanglement, a fundamental aspect that underlies cutting-edge technologies such as quantum computing and quantum communication. Therefore, comprehending the structure of quantum entanglement is essential for both theoretical exploration and practical applications. A key tool in quantifying quantum entanglement is Rényi entropy, a statistical measure that helps assess the complexity of quantum states and the distribution of information within them. This measure is vital for classifying various quantum states and determining how effectively we can model complex quantum many-body systems. Additionally, Rényi entropy plays a crucial role in theoretical investigations surrounding the black hole information loss dilemma, and is frequently employed in studies related to quantum gravity. Despite the significance of quantum entanglement, understanding its nature remains a challenge for both theoretical physicists and experts in quantum information theory. Up until now, most research has been limited to 1+1 dimensional systems, which consist of one spatial dimension and one time dimension. However, delving into higher dimensions complicates the analysis of quantum entanglement structures significantly. In this groundbreaking study, Kusuki, along with Professor Hiroshi Oguri from the California Institute of Technology, Caltech, and researcher Sridhar Pal from the University of Tokyo's Kavli Institute for the Physics and Mathematics of the Universe, employed theoretical methods from particle physics to uncover universal characteristics of quantum entanglement in higher dimensional systems. Their focus on thermal effective theory, a framework that has recently facilitated major advancements in higher dimensional theories within particle physics, allowed them to extract universal behaviors from complex systems. The researchers investigated how Rényi entropy behaves in higher dimensional quantum systems by integrating this theoretical framework into quantum information theory. A critical parameter in this analysis is the replica number, which describes Rényi entropy. The team found that, particularly in scenarios involving small replica numbers, the behavior of Rényi entropy is predominantly influenced by a few essential factors, with the Casimir energy being a central physical quantity in this context. This insight enabled them to further explore the entanglement spectrum, especially in regions characterized by high eigenvalues. Moreover, the researchers examined how the method used to calculate Rényi entropy affects its universal behavior. Their findings represent a significant advancement in our understanding of quantum entanglement structures in higher dimensions, with implications that extend beyond 1+1 dimensions to encompass arbitrary spacetime dimensions. Looking ahead, the research team aims to refine and expand this theoretical framework. While there is still much work to be done, This study is the first to illustrate that thermal effective theory can be effectively utilized to analyze quantum entanglement systems in higher dimensions. By enhancing thermal effective theory with applications in quantum information, researchers could unlock deeper insights into the structures of quantum entanglement in more complex systems. On a practical level, the theoretical insights gained from this study could pave the way for new classification schemes for quantum many-body states, enhance numerical simulation techniques for higher dimensional quantum systems, and contribute to a quantum information theoretic perspective on quantum gravity. This research was partially funded by the Walter Burke Institute for Theoretical Physics at Caltech and U.S. Department of Energy, Office of Science, Office of High Energy Physics, under award number DESC 0011632. Additionally, Hiroshi Uguri received support from JSPS Grants and Aid for Scientific Research 23K03379 and Simons Investigator Award MP SIP 0005259. His research was conducted in part at the Kofley Institute for the Physics and Mathematics of the Universe at the University of Tokyo, which is backed by the world premier International Research Center Initiative, MEXT, Japan, as well as at the Kofley Institute for Theoretical Physics at the University of California, Santa Barbara, supported by NSF grant PHY 2309135 and at the Aspen Center for Physics. Funded by NSF grant PHY 1607611, Yuya Kusuki also received funding from Kyushu University's Ainamori Frontier Program and JSPS Kakenhi grant number 23K20046. Journal reference: Kusuki Y et al. 2025. Universality of Rényi Entropy in Conformal Field Theory. Physical Review Letters. doi.org/10.1103.fsg7q. What are your thoughts on the implications of this research? Do you believe that understanding quantum entanglement in higher dimensions could revolutionize our approach to quantum technologies? Share your opinions in the comments below.